Hi everybody, Dr. Pingle here. We are going to be talking today about regression analysis. This is going to be part one of a two-part lecture, and some of the materials that I'm going to be presenting with today are going to be posted to these URLs. So there's the analysis in GIS repository at GitHub, where the Jupyter notebooks that you're going to see these examples in lecture are things just like it will be in there, and then we're going to be drawing from data that's posted to GeoData. So things we're going to cover today, correlation. We'll talk a little bit about parametric and non-parametric versions of this. We'll be talking about ordinary least squares regression, or OLS regression. This is kind of the most common type of regression. When we talk about ArcGIS applications to this, we'll also be talking about geographically weighted regression, but that's sort of a specific spatially oriented regression. Before we get into that, we're just going to be talking about sort of the very typical case. We're going to be using Python to take all of these things apart, and I'll demonstrate a little bit about some of the cleaning that went into the data that we're going to be talking about today. And the next time we're going to be focusing on using these kinds of tools in ArcGIS, how we apply this stuff to spatially specific data, and especially we'll be looking at residual analysis and again geographically weighted regression. So with no further ado, let's get on with it. My expectation is that you've probably been exposed to both correlation and regression before at some point. Correlation usually makes sense to most people by this point. Regression tends to be a little bit less clear. So I'm going to start off with regression as a way to explain. I'm going to start off with correlation rather as a way to explain regression. The basic idea behind these things is we're looking for the relationship between two variables. So a good example of this is height and weight. Those things go together fairly closely. The taller you are, generally the heavier you are, but only within a degree. So there are people with a heavier weight that are shorter, and people of taller height that are lighter. And so if you took 1,000 people and you measured their height and weight, what you would get is a scatter plot that looks maybe something like you see over here at the right. This is just a simple plot of height versus weight. With a best fit line attached to it that shows how you could predict weight using height. So if you know someone's height, could you guess their weight? And the best fit line would be your sort of best guess of that relationship. When you model that, you get two, at least in this simple case, you get two numbers that come out of the statistics. You'll get an intercept. That's going to tell you sort of what the low value is here, and you're going to get a coefficient weight or a coefficient value here for height. So you're going to take the height and multiply it by 1.1. These are very specific to the units, so this only works for centimeters to kilograms. If you were using inches and pounds, you would have different numbers entirely, but the relationship would still be exactly the same. You may key into the fact that this only works to a certain point. You may notice that the intercept is negative. If you are very short, this will not work at all. So once you get below, let's say 140 centimeters, this relationship doesn't really hold very well. So this is probably only valid for adult height. So these are kind of important things. We'll dig into this here in a little bit. Correlation defines the strength of the relationship. It ranges from -1 to +1. -1 indicating a negative correlation or a negative relationship. Positive numbers indicating a positive correlation, a positive relationship. A positive relationship is defined by as one variable goes up, the other variable also goes up. Negative relationship is the inverse. As one variable goes up, the other variable goes down. Regression then takes the step a little bit further. What we want to try to do is oftentimes describe the equation that's sort of latent in a correlation analysis, but we want to be explicit about the parameters of the model that fits these things. Again, we're really trying to predict one value from another, whereas correlation is really just sort of quantifying the strength of the relationship between those two things. So slightly different emphases, although they are essentially the same process, as we'll see. So for instance, height might be a predictor of weight. We might expect IQ or grit or a combination of these two to partially predict academic performance. If you're interested in that, I've pasted an article here just as kind of a classic example. Ultimately, what we're after here is finding patterns in the data. We want to know whether variables are related, and we might want to predict one variable if we know the values of one or more other variables. We'll be talking about a couple of different data sets. This is one. This is the county health rankings data. We've seen this before. If you haven't had time to take a look at this lately, it's probably worth going to the website, pausing the video, going to the website, and just browsing along. But we will we'll be talking about here these things here as we go. If you download that data and open it up, it looks something like this. This is the 2018 data. You'll notice that there are different versions of this, so as sort of corrections are made to the data set, you might see that these things are stamped with version 1, or you can see in the title that this is version 2. This is a tabbed Excel document. There's an introduction page that sort of describes the layout of the document and what some of the variables are. There's outcomes and factors ranking, sub-rankings, ranked measure data, and so on. So if you can pause the video, download that data, and open it up in Excel, we'll be using this data going forward. This is what that data looks like. We're mostly going to be interested in what's on the ranked measure data. You can see that the structure of this looks something like this. Our top row is sort of an aggregate category. So we're looking at one that's for premature death. Each row corresponds to a county in the data set. Each row has a FIPS code, a state, a county, and then values for these different variables. So for premature death, the key variable indicator here is years of potential life lost rate. And if you're interested in what that means exactly, you can look that up in the documentation. We also, for this one and for many of these variables, provide a 95% confidence interval, meaning how we're trying to quantify sort of the bounds of how sure we are about that estimate. There's a quartile, so the counties are ranked 1 through 4 in terms of where they fall relative to the other counties. And then sometimes there are subcategories of these. So you can see that on this one, for instance, we've got years of potential life lost rate for people who are Black, Hispanics, and people who are white. So let's take a look at the next slide. If we are interested, for instance, in finding connections between variables, we might try to run a correlation between two columns. So we could, for instance, just write in Excel, take two columns that we're interested in this case, the motor vehicle mortality rate and the percent saying that they've had insufficient sleep within whatever bounds that question corresponds to. Maybe it's the last week, or maybe it's the last month, or who knows, we could dig into that, but some metric of how much sleep people are getting. And we might think that these two variables, for instance, are connected. If people aren't getting enough sleep, maybe that's causing an increase in the number of car crashes. And so we can investigate this with a correlation. We can look to see if these things are connected. If we run that correlation in Excel, we get a number that says that these things are correlated at 0.11, which is a pretty low correlation. Positive, right? It is true that as people have less counties that report people having less sleep are also reporting higher motor vehicle mortality rates. We can also look at the scatter plot for this to see how these things are related. So again, we can do this right in Excel, and we can draw a best fit line right on top of this. So we can see again that positive relationship showing up here. That relationship is quantified in a model. So y equals negative 0.26x plus 10.002, and then we have an r squared value associated with it as well. The R-squared value tells you the goodness of fit. It is the square of the R value. So if you just take 0.11 that we saw earlier and square it, you'll get 0.012. Oftentimes we report correlations with an R value. Oftentimes we report regression fits with an R-squared value. And these things are directly related as you might suspect. It's really important not to confuse R and R squared, though. They are, despite the fact that one is just a square of the other, that relationship changes pretty quickly, and you can't just sort of just pretend that an R is an R squared or that an R squared is an R. They're very different numbers. Because R goes from because R goes from -1 to 1. When we square that, they're positive, so R squares go from 0 to 1. But also that strength of the relationship declines very quickly because this number is less than 1. The R-squared value is always going to be less than the R value, and sometimes by quite a bit. If R is 1, then they are exactly the same, but that's the only case in which that's true. By the time you get to an R of 0.8, the R-squared value is only at about 0.65, and by the time R is 0.2, you can see that the R-squared value is probably about 0.05. So that graph kind of captures the relationship there. Even though our R value for our percent sleep against motor vehicle mortality rate, the correlation is 0.11, our R-squared value is only 0.012. And the way that we usually express that is as a percentage. So we would say sleep plays a 1% role in motor vehicle deaths. So not much, not zero, but not much. Another way to look at the relationship between these two things is to look at the coefficients. This is often a way to kind of express things nicely. Our equation here, y equals 0.26x plus 10. The idea here is that 0.26 multiplier in front of the x means that as inefficient sleep increases by 1%, the motor vehicle rate increases by 0.26%. So you can really kind of, that often helps put things in very real terms. Another way to express that again would be something like a 4% increase in a lack of sleep would cause a 1% increase in the motor vehicle mortality rate. What we decide as a strong or weak relationship, there's some guidelines for this. These are very easy to Google, so if you forget, it's quite easy to find these. They're relatively well standardized, and so anything an R value here of 0 to less than 0.2 is described as a very weak relationship. So our connection between insufficient sleep and motor vehicle crashes at 0.11 is definitely a very weak relationship. If you got a correlation value of 0.42, that would fall in the moderately strong relationship. And again, keep in mind that you're looking at the right table, so R versus R squared are going to have different interpretations. One of the big cautionary tales in running correlations is that you really always should look at the scatter plot. The data can kind of come out in very strange ways. In the upper left, we have, this is what's called Anscombe's quartet. These are ways to sort of help explain and explore these kind of weird connections between correlation coefficients and scatter plots. In the upper left plot, we have sort of a minorly noisy relationship between X and Y. But all of these actually yield the same correlation coefficient despite being very different patterns. So the one in the upper right is this kind of curvilinear relationship. In the lower left, it's a fairly strong linear relationship with one outlier. And in the one at the lower right, there's practically no relationship at all between X and Y, with the exception, but because we have this one strange outlier out there, a best fit line will produce a correlation that's spurious. So you absolutely always need to look at every scatter plot that you're running a correlation on. It'll help you avoid making these errors. So we'll be using scatter plots in conjunction with our analyses today. And I would just strongly remind you and urge you to do that whenever you're looking at your own data. This is an example of how we can explore some of those concepts. So here I've just generated some random numbers here. My x values increase from 0 to 10 at a step of 0.5. And then I'm just generating a y value that's related to the x value, but with some noise in it. And if you're interested in how this is done, I've pasted the Excel formula for that here. Essentially, just creating a y equals x squared kind of a relationship here. If I want to try to run a correlation on these, the correlation again by default is always just a straight linear fit, and so I would produce an r squared value off of that correlation. If I were just plotting this linearly with the black line here, that r squared value is 0.9184. But you can see that doesn't actually capture the data very well. If I try to model that with a polynomial fit, as you see in the orange line and in the box at the upper right, my fit on this data increases to 0.9868. So it goes from 0.91 to 0.98, or 0.92 to 0.99 if we're rounding it. That's a significant increase, and that significant increase is happening because we're choosing a more appropriate kind of a fit for our data. And this ultimately is why correlation analysis is worse than regression analysis, because correlation, it's very easy to take a regression analysis to fit a more complex model, even just slightly more complex model, like you see here, get that r squared value and to turn that into an r value that's a little bit more meaningful. But if you don't look at the data and if you don't try to fit a better model, you're oftentimes going to be just only very coarsely capturing the relationship between these two things. So quick and dirty correlation is easy enough, but a regression is only just mildly more work to do. So I would encourage you to, just as I'm encouraging you to look at the scatter plots, to start thinking about running regressions rather than just sort of running correlations. One of the hitches in this is the relationship between these things. So I've shown you a curvilinear relationship in the last slide. A lot of times data is doesn't necessarily fit a neat mathematical model. The data that we capture may not be really numerical anyway. And so in some cases, what we want to do is we run statistical tests that accommodate outliers or strange relationships in a way that doesn't happen when we sort of run the traditional parametric tests that assume that your data is distributed normally. As we've talked about a number of times before, geographic data is often not distributed normally. And so you need to take kind of extra care to look at that, to look at those distributions. We'll be talking more about that at the end of lecture here today. In this case, we're looking at two different plots here. In the upper left, we have this sort of S-shaped curvilinear relationship. It's monotonically increasing as x increases, y always increases. If we run a correlation on that, if we try to fit a best fit straight line, we'll get a correlation of 0.88. But if we run this with what's called a non-parametric test, where instead of using the actual values, we essentially transform the values into ranks, highest value, second highest value, third highest value, and so on, and then run the correlations on that, which isn't exactly true, but pretty close to true. What we get here is, what we would get with that is a correlation of 1. So the Pearson correlation value, sort of the default one, the traditional one, that would yield a value of 0.88. If you run this non-parametric test, you actually capture this relationship better. It is a perfect relationship. X is directly related to Y. There's no noise at all. Because the relationship is more complicated than just a straight line, the Pearson correlation doesn't capture it quite right. This is one of those things that's not terribly easy to do in Excel. If you need to kind of approximate this, you can just calculate the ranks first and then run correlations on that. But this is kind of one of the reasons why, while Excel is a great tool and you can do a lot of quantitative and statistical analysis in it, it pays to start learning a little bit stronger data analysis techniques, whether it's in ArcGIS or whether it's in Python or whether it's in a combination of the two. So to illustrate this, I've generated some more data here. You can see we're generating values here in Python ranging from 0 to 10 at 0.5 increments. So that's the top line there. The second line essentially adds a relationship between those two. So y equals x squared plus a little bit of random noise. So you can see that the expression there at the end is adding some noise to it to make it not a perfect relationship. We can plot that out, and then if we run those parametric and non-parametric tests, what we find is that the Pearson test in this case gives us an R value of 0.957. So that's the parametric test. The Spearman test, because this is curvilinear, is going to be a little bit more reliable and is going to capture that relationship a little bit better. So you can see that the Spearman non-parametric test is yielding a correlation of 0.99. Now you can't just run the test and pick whichever one is higher. So that's bad form. You don't want to do that. But if you've got something funky in the relationship between your two variables, and you don't want to sort of explicitly make a mathematical model to do that, a non-parametric model is often a good way to start. So if we want to, one of the things that I guess I would urge you to do, so non-parametric tests are good if, again, if you don't want to try to capture the math, but how would you want to capture that math? How could you capture the math if that's what you wanted to do? So here we have some X and Y data. You can see that that Y is essentially close to doubling every time. That's not quite right. There's some noise in the data, but that's close to true. Whereas X goes from 0 to 1 to 2, 3, 4, 5. If we plot that out, we get a relationship that looks like that. And you can imagine that if we just run a correlation on this, we'll get a positive number. Indeed, if that's all we want to do, we can use a program called Seaborn, which is a Python package dedicated to visualization that also includes some helpful statistical support. We can use Seaborn to sort of run some simple analysis and to see the results. So you bring this in with import Seaborn, and then you can use Seaborn objects and functions. So seaborn.regplot for regression plot. You pass up the X and Y data that we had before, and we get not only a scatter plot, but a best fit line and what's called a confidence interval, sort of shading how sure we are in our estimates. One of the things you might notice about that confidence interval, first of all, about the line, is that it kind of cuts through that curved feature. It kind of captures the relationship, but not perfectly well. You've got some bias. It's undershooting at the ends and it's overshooting in the middle. So this isn't a particularly great fit. We can get the exact quantitative value. We can run a regression with this model this way. So here we're using a package called stats models to bring in a feature here called SM. We brought our stats models as actually this is stats models formula as SMF. So we're using our statistical package here. We're calling a function called OLS for ordinary least squares. And then we're defining a formula, y tilde x, which means that y is related to x. You can imagine that tilde is kind of an equal sign. And then we're passing in our data frame here to fit the data. And then we're calling a function on that object to fit it. So it's a little bit of a dense line of code, but it's pretty easy to imagine what you need to swap in and out to make it work. If you run this, what happens is you get a results object back, and you can print that results object out. And actually, there are a number of features in here, including residuals and statistics about the fit, that you can dig into if you want. But one of the things you're likely to want is just to print out the results summary. So here we're getting the results back. We're printing out a summary of the results, and that's what you see in the screen here down below. So we've got a couple of things to talk about here. In the upper right hand of the result, we get our R-squared value. So our fit here, our R-squared value is 0.824. A lot of times you'll be encouraged to report what's called an adjusted R-squared statistic, which is 0.78. I'm not going to get into the details of that now. Essentially, the adjusted R-squared is going to sort of take into account some, let's just call them weirdnesses in the data that the regression has discovered. And so typically we'll often report this adjusted R-squared. But for the purposes of this exploration, you can see that they're both relatively high. They're usually going to be within a couple of percentage points of each other, depending on your data. We're also getting back the coefficient value here. Let me see if I can get a pen and mark this up here. So here are our R-squared values. Our coefficients that we're working with here are here. So these are the coefficients of the best fit line. We have our intercept of negative 11.57, and y equals, this is our y equals mx plus b, this is our b, and this is our m. So this is our m. So as x increases, y increases by a factor of 17 times x. One of the things that's going on here that we need to talk about is this. So the formula that's describing the relationship is probably the most important part of this code, and also probably the newest and the strangest. So let's dig in here a little bit to talk about what that is. Y tilde x. What this is an R-style formula built on a package called Patsy. And so one of the nice things about this is that the sort of nomenclature, the way that these ideas are expressed, are now the same in R as they are in at least this package in Python. That's pretty handy. A lot of people are kind of coming from the R world, or they bounce back and forth between R and Python, and this helps keep things a little more standardized, which is really nice. Here, by the way, are the import statements that we didn't get a chance to talk about. So here we're importing statsmodels.api as SM. We're importing statsmodels.formula.api as SMF. And we can use those objects then to run our statistics. The Patsy language is a little bit weird. So the documentation is here if you're interested. I'm not going to get into a lot of this today. I think we can probably get through most of it by example. I guess I would caution people that the expression that you write is not can be a little deceptively simple, and so it takes a little bit of practice to get used to it. But I think we're going to cover most of the general cases today. So this is an example of applying a different kind of a fit. We're applying here a polynomial fit. I had said that the data that we had created was, well, you could kind of imagine it being captured as kind of a squared relationship. If we wanted to assume that that was true, how could we express that idea? And we could express it this way. So our formula becomes y tilde x plus, and then capital I, parentheses, x squared. The reason we have to do this is because the x asterisk asterisk means something in particular in Patsy. It describes a different kind of a relationship, and so the I essentially means I want you to treat this as a mathematical expression, not as your kind of native Patsy language. So so what this is doing, and there's always an intercept, so you don't have to specify that. So y equals, at least there is unless you declare that you don't want one, but y equals x plus I x squared. What we get here is if we look at the coefficients, so on the lower right here you see that model expressed as kind of a traditional algebraic formulation, and you can see the fit in the scatter plot there. And then the coefficients at left here, you can see those in the table. Our r squared value, we'll kind of mark this up here, our r squared value for this fit is 0.99. So quite high. We're capturing this relationship much better than we were with a simple straight line. The other thing that I would direct your attention to here is the way that we're getting our best fit line right here is we're actually interpreting the values of our predicted values off of our original ones and using this results object to predict them. So this is one of the things when I said that when you get results back, here we're just looking at the results summary, but that results object is actually quite powerful. And so here we're using that results object to create y values from our x values. So again, I don't want to get too far into the weeds here, but this results object has a lot of stuff in it that you may find useful. This is an example of an exponential fit. The way that you declare this in Patsy looks something like this. So the log of y equals x, slightly different formulation. You can see that we're still getting a fairly good r squared value, and the fit again is quite good. So there's not a lot of difference here in terms of how well our exponential fit works versus our polynomial fit. They work almost exactly the same. If our data took slightly a different form, or if they continued on, we might see some divergence in these two models. But it's not too uncommon to find out that two different fits produce similar results. The way to extract that fit is a little bit more complicated. So if you're interested in this, I'll let you pause the video and kind of digest that. The expression here is just a little bit trickier. But essentially, again, we're just sort of taking x and we're trying to fit it to the log of y. A kind of a companion fit to those is the logarithmic fit. The expression for this looks something like this: y equals the log of x, so slightly different expression. In the exponential fit, it was log of y equals x. We have to unpack those in kind of a different way. This is a different number set, so this isn't the same number set as we were working with before, but you can see that this is capturing this relationship reasonably well. And the power fit, again, is slightly different. Again, we had to use sort of a different data set. That data set is taken here from Leonard and Robinson, and they cite Marcus Hamilton. You can track this stuff down if you're interested. But essentially, the expression here is the log of y is equal to the log of x. And then again, unpacking these parameters, it just becomes a little bit different, but captures the relationship fairly well. Those are the main kinds of models that you're likely to work with. So linear, polynomial, exponential, logarithmic, and power capture in most cases of the data that you're likely to fit. You can get as complicated as you want, but you probably won't go too wrong if you just use those five. Because those are kind of the core things, it shouldn't surprise you to see that Excel can do those as well. I really strongly encourage people to use the data analysis packages that they're comfortable with. You should try to develop your skills, and so working with Python is good. But if Python is kind of proving to be too thorny, don't feel bad at all about using Excel to process through this data. It may take a little bit longer. It may take a little bit shorter. It's probably easier to run a simple regression, a simple single variable regression in Excel than it is to run it anywhere else. So don't feel too bad about using this. I put some screenshots in here to help kind of describe where these things are. If you create a scatter plot, you get access to a trend line. If you open up the more trend line options, you really do get a large number of fits that you can use. You can set the intercept, You can display the equation, you can get the R² value. So a really fully featured way of running a single variable regression. So we're going to proceed here. That's kind of a look at sort of some very simple data. Let's use the county health rankings and an election data set to explore some real connections between variables. All of these things, again, are located online. So if you go to the GitHub Analysis and GIS repository and the GeoData repository, you can download the data that we're using for this lecture. You can run these things yourself. You don't have to type in sort of the code that you see on these slides. In most cases, the templates for those will already be there for you in the notebook. So I would encourage you to, if you haven't already, to download the notebooks that accompany this lab. They're under Regression, or this lecture. They're under Regression, and just kind of use those in tandem with the lecture as you go through. Okay, so before we dig in, a couple things I want to point out about the data. So one, when you download this, when you download the Excel files, it looks something like this. While this is really nicely laid out to sort of browse, it's really pretty bad for data import. So trying to get this into any kind of a package for data analysis is going to be tricky. We're going to talk a little bit about how to do that with Python. And there are many ways to solve this problem, but I want to bring this up because data cleaning is again, just a really critical part of the job. You should just expect that data cleanup is a part of pretty much any intensive project that you're ever going to work on. And so it's not something to be too upset about. It's just a really a normal part of the job. If you go to download the data, you'll notice that there are a couple of different versions of this. There is a CSV analysis layer that comes in that looks something like this. This is much more nicely laid out for statistical analysis, and indeed that's what the point of this is. There aren't any county labels. There aren't any state labels. Why is this? Mostly because it's redundant information. You'll see that when I bring this in Excel, that my FIP state code has been reduced to a one-digit number. That's not true. If we had scrolled down, we would see the rest of them. But the state FIPS codes are 2 digits long, and we're only getting we're dropping the leading 0, just like we're kind of used to seeing by now. And same thing with the county FIPS code. The leading 0 has been dropped. But kind of critically, we're missing that combination of state and county, which is really helpful. Each row is tagged with the year. Actually, that's pretty nice if you're doing a multi-year analysis. A little less useful for what we're doing. Obviously, you can see that 2018 is filled in for the same on all of these. But if you're importing county health data over multiple years, it's nice to have each of these rows tagged with the year. And then all of the different variables are tagged as measure underscore and then a number and then value. This is to make it a little friendlier to ingest into a system. Those file names are pretty long, so you can see that if you tried to export this back out again in ARC to a shapefile, it's longer than the 10-character limit, and so you'd start dropping parts of this again. The other issue is that they're coded values. If you go to download this data, you'll see that there's an additional PDF that comes with this that will describe what all of those variables are. So this is the way researchers would usually use those. Is they'd download the CSV data. They would look at the variable code. They'd look that up in sort of a dictionary, and they'd pull that open. And you've probably seen this before with the census data, where the variable names are encoded, and you've got to sort of use a decoder PDF to figure out what they are. If you download the CSV files and bring them in, they import really easily into pandas. So this is an example of that. The problem is, relating these things back to which measure is what is quite annoying. And so we're going to take a different tack on this. Before we do, just a quick scatter plot here. This is what that would look like. You could just plot one variable against each other. And again, if you look this up in the PDF value, this is not such a bad way to do it. We'll talk a little bit more about Seaborn as we go. Seaborn is a package that's mostly a data visualization package. It has a lot of really nice sort of regression support functions in it. This is an example of plotting just those variables, insufficient sleep and motor vehicle mortality rate, against one another, and then using the reg plot feature in Seaborn to do that plot. This syntax is actually a little bit old. It used to be that Seaborn would get imported as a variable SNS. These days, the import is often just import Seaborn. So some of these examples will be a little bit mixed as the conventions have changed. I wanted to try to retain some of those variable names. I think it makes it easier as you're sort of exploring data and processing data. I don't expect you to process all of this, but what I wanted to do was sort of make friendlier variable names that when I loaded this stuff into pandas, things make a little bit more sense. So rather than using the CSV in a code book, I wanted those names to be really nicely accessible right in the file. You could do this by hand. There's about 200 columns, so that would take a long time. It would be very annoying, and so rather than do that, writing a little bit of programming to kind of read these in can pay off. So this is an example of a read county health rankings data. I give it the Excel file that I downloaded, and it processes it and turns it into a data frame for me. And I just, because I've done this enough, it was useful for me to be able to do this in an automated way. So you don't have to do this, but you may want to pause the video and sort of see how much of this you understand. If you do this, you ingest sort of a standard county health rankings Excel file, and what you get out is a more nicely formatted data frame that looks like this. Now all of those variable names are directly readable right in the column headers. If you want to see a little bit more about this, we're just going to be using these sort of repaired values kind of moving forward. If you want to see how this stuff works, all of this is posted to the GeoData repository on GitHub. And there's a couple files in here, one for how they were created. So if you want to see how that data ingestion process worked, it's there. And then there's a second one here looking at county health rankings data, how you can use those data. So a couple of quick sort of helper notebooks moving forward. This is an example of what the creating county health rankings dataset notebook looked like. It's got that read CHR data function in it. You're welcome to borrow that if you want. It's got a little helper function called friendlify that removes a couple of special characters that kind of interfere with data processing. So feel free to browse that as you like. This is an example of using the data set. Again, I wanted to package these Jupyter notebooks along with the cleaned data just as an example and as a documentation of how this was done. So we're going to take a look at a couple of examples here. I'm going to use a package called stats models, which we're bringing in here as an SMF variable. So SMF is our stats models functions. And we're going to be using a sub-function here called OLS, ordinary least squares regression, to do the analysis. We've loaded, basically, you can find this stuff on the, if you want to follow along with this notebook again, it is posted to the analysis in GIS repository linked as part of the course under regression. So here we've loaded in our data frame for the county health data, and we are just plotting. All we want to see here is just what we've looked at already. We want to plot insufficient sleep with motor vehicle crash deaths. All we have to do that, we're sort of defining X and Y as variables, which are actually strings. We use those strings to index into our data frame, and then we essentially pass that data into the stats model's ordinary least squares function. We define our formula, and we fit the data. So it's fairly dense lines of code right here. You know, it's only a couple of lines of code to actually do this work, plus a couple of lines here to define our columns. But they are fairly dense. And so I would encourage you to spend a little bit of time looking at those so you can sort of interpret what they mean, see if you can follow along. These X and Y are essentially being pulled out of the other, these X and Y strings are used to index into our county health rankings data frame and then populate, in this case, an OLS data frame. So this is actually a data frame. And then that's what's used in here. And these variable names are now X and Y. If we run that simple regression, so again, we've seen this done in Excel, so we're going to get the exact same numbers here, but now we're using Python to do it. So you can see that our R² values are the same, our intercept and X value are the same, and so we're essentially using these two pieces of information and a third that we'll talk about later, the P value here, to interpret the data. There's a lot of other extra features here. There's information about the number of observations. There's information about the degrees of freedom. There's information about the normality of the data. There are tests to figure out how normally distributed our data are. Lots of different things here to unpack and interpret. But all I really want you to focus in on here, again, we'll use a different color, essentially focusing in on the R² values, focusing in on the coefficients that are associated with our variables, and then focusing in on the P values. This again is our scatter plot. So this is the one that's created with Seaborn. One of the things that we might want to do, so we've covered sort of the simple case. I want to fit one variable against another variable, and that's still a very common way of doing regression, right? And if as far as you get is sort of being able to run a regression of one variable against another, that's not too bad. But oftentimes what we want to do is run more than one variable against a dependent variable. So the idea here is we're interested in a particular phenomenon. So in this case, we're looking at some election data that we've brought in. The full code to this is again online with the class notebooks. If we're trying to explain an independent variable, a dependent variable here, so our dependent variable is our Y variable. This is the GOP percentage minus the Democrat percentage in 2016. This is a measure of how Republican a county is. And we've merged this with our county health data, and we want to try to explain whether a county had a strong Republican vote or a strong Democratic vote or a mild vote. We want to explain that from some other demographic variables. And so the county health rankings are full of demographic variables. You can look at those and you can see what you think might be fun to plug in here. I've picked 3 that seem plausibly related to how a county votes. One is how rural or urban it is. This is a percentage of the population that lives in a rural area. The percentage of the population that is 65 years old or older, as a second explanatory variable, and the percentage of people that answer that they've had some college. These are 3 different explanatory factors, and we could run each of them individually against that, and we could get a regression result, and that would certainly be one way to do it. We could look at things like the R² value for each of these, and we could look at the coefficient fit for each of these. But one of the nice things that we can do is we can actually run this all in a single model. So rather than running 3 separate models, we can combine these variables into one single model. And that helps us sort of see how close we're getting to explaining this phenomenon that we're interested in, the percentage of vote, how Republican a county voted in the 2016 election. The way that this is done is pretty straightforward. So we've seen a couple of examples of running single variable regressions. This is how the multiple regression is run. So multiple regression meaning multiple explanatory variables. So y tilde x naught plus x1 plus x2, that's our model. So a slightly different format. Instead of just one single dependent variable and one independent variable, we now have 3 independent variables all working together to explain our output variable. Our result has similar sort of things that I want to pay attention to. One is our R² value. So we're explaining about 24% of the variance, 24% of the variability of how a county voted is related to how rural it is, how much of the population is over 65, and how much of the population has had some college. So we're starting to get a pretty strong model here explaining voting patterns. And if you want to dig into all 200 different variables in the county health rankings, you can try to explain this even further. As we add variables into a model, what you will find is that the R² value will always go up. It can actually pretty much only ever go up. The more numbers you throw, or the more variables you throw in there, the more that's going to go up, but not by an even amount. So you can add a variable in, and maybe it adds 10% to the R². You can add a variable in, and maybe it's a really good one, and you explain 20% more. But maybe you add another variable in, and it increases the R², but only by a little bit. Maybe it increases it by 0.0001%. In that case, we probably don't want to keep it. And so you're always going to balance things as an analyst and as a modeler between sort of trying to get a better R², meaning a better explanation of my dependent variable. And you want to balance that against the simplicity of your model. So if I threw all 200 variables in, I could definitely do that. But the result would be a very complicated model that probably tops out anyway. It'd be interesting to kind of see where it tops out. But you're never going to get to 100% anyway. It's going to top out at a certain point. So we want to have sort of the fewest number of variables that sort of still explain our phenomena. The other thing that I want to look at, though, is this P, this column P. So far we haven't paid a lot of attention to that. In fact, if you look at this, we're getting P values that are all very small. It's reporting a P value for the x0, x1, and x2 variables as 0. That's actually just a rounding thing, as we've talked about before. So those numbers are small, but not actually 0. The intercept is 0.008. All of these are sort of under that. P is less than 0.05, which is sort of our general standard in statistics to describe whether we think that variable is statistically significant or not. All of these things are statistically significant. All of these numbers are below 0.05. So all of these things have a place in the model. So other than sort of broad concerns about parsimony, the other major quantitative criterion is checking to see if that p-value is being reported as 0.05 or less. One of the things that you really have to look out for, though, which we haven't done in this model and which we will in the next slide, is to include interaction effects. So interaction effects are this really interesting phenomenon where one variable can sort of translate or change the relationship. And in extreme cases, it will actually invert the relationship. So I've attached a link here for the Wikipedia page on interaction. I would encourage you to follow up on this if this isn't clear. But I think one interesting case explains this fairly well. So if I'm building a model to try to figure out the degree to which a person says they care about whether sea level rising by 20 feet, you can imagine that there are a number of different correlates that might correspond to how a person answers that question. Age might correspond fairly well. You might well imagine that younger people maybe care more if sea level rises than older people. That could be true, that could not be true. We could look at the data and find out. In fact, the link to the original article here is here if you're interested. But we're looking at two variables as part of our model. In this case, we're looking at whether people say that they have completed a certain amount of schooling. So whether they said they've completed high school or less, or some college or postgraduate studies. And a second variable, which is their political ideology. And we could imagine both of these things on a quantitative scale. They're sort of qualitative variables, but they exist on a spectrum, and so we can code these quantitatively. What we find when we run a model, a regression model, to try to fit this data to this question of how much they care about sea level rise, there's an interesting interaction, which is to say, you might easily sort of expect that whether that political ideology corresponds to whether people answer this question or not, and it does. But interestingly, that political ideology also moderates how much college influences the result. So you might expect that the more college someone has had, the more likely they are to care about whether sea level rises by 20 feet. And if you just run that correlation, you will probably find out a positive association. However, if you look closely and run this in concert with an interaction effect on the ideology, what you find is that ideology actually inverts that relationship. So people who are extremely liberal or moderate, if they've had more college, they're more likely to care about sea level rise. But the inverse is true for people that say that they're extremely conservative. For people who say they are extremely conservative, more college means they care less about whether sea level rises by 20 feet. So this is what we mean by an interaction effect. It can actually reverse the effect that another variable can have. And so by not taking this into account, you're missing a really important dimension in your data. So including interaction effects is pretty easy in stats models or with the PATSI language. Essentially, all you need to do is put in the asterisk, which is shorthand for including both of the models plus the interaction between those models. If you just want to write an interaction, you can use the colon operator to do that. Keep in mind that these are not mathematical operators when we're talking about this. These have very specific meanings within PATSI. So we're not adding them together, we're not multiplying together. We're using those mathematical symbols as shorthand to mean relationships that are not actually mathematical. So just keep that in mind as you're looking at when you're looking at these language, this expression of the language, which is pretty common. It may seem a little bit arcane, but it's getting to be a fairly standardized way of expressing these statistical relationships. If we make an adjustment to our model, then we can run these interaction effects pretty easily. So our formula now looks something like this: y equals xo interacting with x1, interacting with x2. So they're all interacting together. And when you run the result, you then get, instead of just sort of the intercept plus the three variables, you get all of the combinations of those as you go. So you get xo, you get x1, you get the interaction of xo and x1, you get x2, so you get the interaction of xo with x2 and x1 with x2, and then you get the interaction of them all together. And you get an r squared value for that. And when you when you run those interaction effects, you get an R-squared value of 0.27. So we're starting to explain a little bit more about our data by including these interaction effects. But as I've said, you don't want to look at these things in isolation. You want to look at them in combination with their coefficients, which I'll highlight here, and with their p-values. And what I want to focus attention on is the p-values specifically. So, well, actually, let's start with coefficients. In this expression of the model, what I'm finding is that XO, which corresponds to how rural they are, the more rural the population in this model, the less likely they are to vote Republican. In this one, the older the population, the more likely, you can see that this is a positive, the more likely they are to vote Republican. And X2 is here. The more college they've had, the less likely they are to vote Republican. So what you get is sort of this interesting inversion, maybe than what you were expecting as far as the rural, when you include these other factors, when you kind of parse these things out. Now, apart from the signs of the coefficients and actually the quantities, which we've talked about earlier, the probabilities are important. So which of these probabilities are less than 0.05? Only two of them, actually. This one and this one, which corresponds to X2. So college is showing up as statistically significant, and the interaction between rural and college, which is showing up as statistically significant. Maybe because it's having that sort of mitigating effect that we saw with sea level rise. Some of these p-values are actually quite high. So which ones are really high? Lots of them are pretty high. This one is pretty high. So the interaction between all of these is not statistically significant. The interaction between X1 and X2 is not statistically significant. And this one is also fairly high. Urban-rural is not statistically significant. So even though we had this sign over here in the correlation coefficient, because this p-value is actually pretty high, it means we don't really tend to look any further at that value. We would tend to discount that in our final model. Now, what we tend to do is we do this in one of two ways. One is if we have a lot of variables that we're interested in and a lot of interactions, we sort of successively add those into the models to see what seems significant. Or we throw the kitchen sink at it and we throw everything in there, and then we start one by one removing things until only the things that are left are significant. So those are the kind of two stepwise approaches to building a full-featured multiple regression model. So this is a pared down version of that. So instead of just specifying XO times X1 times X2, where we're throwing the kitchen sink at it, we're now keeping only this one, this one, this one. We're keeping our original variables, plus the interaction between rural and college education, and the interaction between age and college education. And we're just throwing this in here just as an example. When we do this, you can see that the p-value for rural is significant. College becomes significant. The interaction between rural and college is significant. But in this formulation of our model, both of these are not significant. So the next step would be to sort of eliminate this from the model and then to check it again. So there's a bit of an art sort of kind of adding things and subtracting them and looking at the results. And so it's not a cookie cutter kind of a turn the crank, one size fits all approach. It definitely takes some practice and some skill to be able to pull off a multiple regression with interaction effects. But that's the kind of thing when you're taking kind of an advanced statistics class in graduate school, they'll likely get into a little bit more. This should sort of give you the tools to at least interpret what you're getting. First, look at the p-values to see if they're statistically significant. And then if they are, and only if they are, look a little bit further to see this and try to create models essentially where you're minimizing the number of statistically insignificant items, either by kind of slowly adding more variables in or by pulling values back out. I tend to add values in rather than take values out, but it's just a difference in sort of philosophy of modeling. Okay, one last topic before we wrap up, and that's checking for normality. So the gist here is that whenever you're working with data and you're running these kinds of tests, so many of the tests that you're used to running, whether it's regression or whether it's t-tests or correlations, are all based on the assumption that your data is distributed normally. If that's not true, then you need to either do a data transformation to try to make it more normal, or you need to use a non-parametric statistical test to find that answer. But the very first step is deciding whether what you're looking at is normal or not. And so as an example of this, this is taking that county health rankings data and looking at just one of the variables. This is physical inactivity %. You can plot this out for all of the counties and you can get a result, and you can see just visually, even before kind of getting into the details of this here, visually, does that look like a normal distribution? Does it kind of look like a pyramid with a rounded top? Yeah, totally. That's a pretty normal looking distribution. Median household income, however, is not. So if you look at this, it still sort of has that pyramid, but it's got this long right tail. So it sort of is all bunched up at the lower end, and then it really kind of tapers off slowly on this end. So this is called a long right tail. And what that means is that our data is really not distributed that normally. What we need to do is we need to transform this, or we need to use non-parametric statistics to process that data. And in the case of geographic data, a log transform is often the easiest way to normalize your data. And that would take care of this problem quite easily. There's a slightly more technical way, other than sort of eyeballing a histogram, which is to use what's called a QQ plot. So this is a quantile plot. We are plotting our distribution against either another distribution, or generally speaking, a normal distribution. What you get is something, in the case of our, actually, I'm not sure whether this is the income data or not, but for whatever this variable is, we are over predicting at the ends, and we are under predicting at the middle. So the big departures from the red line here in sort of a systematic way. It's not the noise of it that matters. It's sort of the overall pattern. The fact that it doesn't match this red line means that we've got some non-normality going on here. For the graduate students, it's often good to look at more formal tests of normality. So if you're writing your dissertation, it's generally not good enough to just sort of eyeball a histogram. You're going to want to run a real statistical test on this. There are a variety of tests that do this. This is one of them. If you have an interest in that, definitely come talk to me. And this one is actually a pretty common one. And I forget how it's pronounced, Jacques Barra. But this is one technique among many to quantitatively assess how normal your data is. So that was a pretty long technical lecture. You might need to stop and go back and relook at some of that stuff, and that's great. Work with the notebooks that have been provided. I really strongly believe that the best way to learn this stuff is to kind of work with the data, to tinker around with the knobs, and to see what happens as a result. And so those notebooks can really help you make this part of the lecture very interactive. So a couple of take-home messages. One is it's important to me that you can use Excel to dig through some of these easy cases. Excel is a ubiquitous tool. It's really easy to access. Everybody these days has access to Excel, it's easy to bring your data in, it's easy to sort of eyeball problems with it. And so oftentimes I use Excel as a first cut to just look at variables. It's faster than loading the data into to Python and really easy to do some simple regressions. But when you start getting into the more advanced stuff, if it's part of a larger project, that's when you're going to want to try to script things, when you're going to want to use more sophisticated tools. I hope that in this class you're getting introduced to using some more of those tools. It'll take a little time for your comfort level to get up there, but the more you practice, the more comfortable you're going to be with this stuff. A couple of the tools that you're going to want to use, pandas to get your data in and out, matplotlib like we've used a number of times before, but Seaborn comes in extremely handy for very quickly drawing scatter plots and best fit lines, and then running OLS regressions with stats models is sort of a bread and butter kind of a data analysis technique. One final note as we wrap up here, and that is that the kind of where you go from here is up to you. Increasingly, a lot of these statistical tests are being envisioned as a single, what's called a general linear model, a GLM. All of these statistical tests that when you take a stats class, you sort of learn these things in parts. This is a sometimes confusing way for students to learn how to do statistics and process statistical data. In contrast, a kind of unified approach to doing this is to basically model everything as if it's a linear model, whether it is or not, whether it's continuous or not, whether it's categorical, whether it's parametric or not. You can basically use this one technique to get pretty far on these things. Now, I didn't learn statistics this way. Most of the people that are teaching statistics didn't learn it this way. The number of people that in turn teach it this way is a little on the low side. And in this class, I've tried to simplify things as possible. I think that there's a couple of approaches that are really powerful. Running t-tests is very powerful. Running regressions is very powerful. And to my mind, if you're going to go further with that in statistics and data analysis, then this is definitely the way to go. If you're not, having just a couple of categories of tests to run can make things a little bit easier. So regressions and correlations will probably take care of 95% of all of the data that you're going to want to analyze. T-tests will probably take care of 4% of the 4% more, leaving you with just a little bit left. And at that point, you'll have to do a little digging and figure things out from there. But I do find this a very valuable resource. This page has how to run statistical tests in both R and Python. It really tries to unify both of those worlds. So really nice blog, and it's something that I personally use somewhat often. So with that, we'll wrap things up. It's a bit of a long lecture. Thanks for tuning in, and we will see you next time, where we'll be talking about running some of these techniques within the ArcGIS universe.